Hello and welcome back to Calculus 1, section 4.3 on first and second derivative tests. So we are going to look at various qualities of the graph. So let's draw a graph in XY coordinate system. It doesn't really matter what that graph looks like. We are going to have a maximum point. We'll put that as x1. Minimum point, put that as x2. And there is a point here somewhere. We'll put that one to be x3. We'll see what those are. So now, what are the various things that we want to talk about? Well, let's start first with the notion that all of this, right, the graph has the domain from negative infinity to positive infinity, and that the graph is either above or below the x-axis, right? But we can describe the portions of the graph just by looking at x values on the x-axis between, right, two values. So we are going to take the graph like that. So these two parts are when the graph is, right, f of x is increasing. And we can use the color code here to say that on negative infinity to x1 union x2 to positive infinity, f of x is increasing. We are going to use first derivative test to get those together. Now let's switch to, let's say, this light blue and go for this part here, and this we're going to be decreasing. So the light blue part is where we say on x1 to x2 interval, f of x is decreasing. So these concepts should not be difficult to understand, because the graph is either going up as you move to the right, or it's going down as you're moving to the right. Now we're going to take a look at two new concepts which you haven't dealt with before, and that is the concept of this orange part. And the orange part is going to go like this. Oops, that's too much. Come on. There we go. You have to end at x3. So this part of the graph ending at x3 is called concave down. So the orange here, which would be on negative infinity to x3, f of x is concave down, meaning something like that. And then we're going to have one more. Let's use green. On the other side of x3 going to positive infinity, we're going to call this concave up. So we have the green, and we'll say on x3 to positive infinity, f of x is concave up. So these are the parts of the graph that we are going to discuss today. Increasing and decreasing will be dealt with the first derivative, and the concave up and concave down concept would be the second derivative test. And we will present our answers in terms of the intervals which are on the x-axis. So we will never involve any y-axis values, any y values in our answers. So just the x intervals from x value to another x value, and we'll go from there. So this is what we are talking about in 4.3. So let's deal with the first part. The first part is called the first derivative test. We call that FDT for short, so we can quickly deal with this. So we start with a statement, and here we go. So number one, if f prime of c is less than 0 on some interval a to b, which is obviously on the x-axis, then f of x is decreasing on AB. Actually, I'm going to move this decreasing so I can put the cloud around this. So it's decreasing on AB. So if the derivative is negative. Now, we already talked about this all the way in chapter 3, section 2, I believe, where I said that if the function is decreasing, you have a negative derivative. So now we're just having the statement in a theorem. If f prime at some value c is larger than 0 on, again, some interval a, b, then f of x is increasing on AB. And finally, number 3, if f prime of c equals 0, then x equals c is a critical point, which means min-max, or maybe something new, inflection, which we are going to define in about 20 minutes. I'll put this on the cloud. This is your first derivative test. We find critical points, we partition our domain, and then we pick test points. Those are the test points C. So let's just write a couple of notes. So C's in the theorem above are the test points we pick in each partition. Partitioning of the domain is done by critical points and vertical asymptotes. Now, all of this in purple will make more sense once we start working on the example, but we are technically done. And then later for the second derivative test, you will see that it's cut and paste the first derivative test, except conclusions are different and you're using second derivative instead of first. Okay, so let's do an example. We're going to start the example using a function that we know. So let's go with x squared minus 2x, for instance. So let's say we are going to talk about f of x equals x squared minus 2x. So this particular function is the quadratic function, and we can quickly figure out, the vertex and all that stuff, but we don't need to, because once we start solving this function, we will quickly find everything that we need in terms of when we do the first derivative test. We will quickly find out everything we need for the graphing and so on. So the first derivative test starts by taking the first derivative, in this case 2x minus 2. We set it equal to 0, and we get x equals to 1. So now we have x equals 1, and we know that's our critical number. There are no vertical asymptotes because it's a polynomial. So the only partitioning that we are going to do for the whole domain, right? We can also say negative infinity to positive infinity for the domain. So now, if I am to make the partition, the only partitioning I'm doing is at 1. From negative infinity to positive infinity, I only have 1. So now, we pick any value we want in each one of the regions, and we pick 0 and 2, and those are your test point C. So here is the first derivative test. You take f prime computed at 0. So your test points are 0 and 2. Let me write that in blood over here. So test points C. C equals 0, C equals 2. So those are the test points that we are using to plug into the first derivative to come up with values. So now we have f prime. F prime, we know it's 2 times 0 minus 2 because it's 2x minus 2. 0 minus 2 is negative 2. That's less than 0. And we know from the theorem, because we just did the theorem, right, that if the derivative is less than 0, the function is decreasing, right? Oops. F of x is decreasing, so we are going to put an arrow like this in the first partition that tells us that we have a decreasing f of x. Now we calculate f prime of 2, which will be 2 times 2 minus 2, which is 4 minus 2, which is positive 2, which is larger than 0, which from the theorem we just learned, right, says that the function is increasing after 0. Oh, sorry, after 1. So now we have found the intervals of increase and intervals of decrease. So here is the answer, right? One that you are providing for the full credit. You will say or you can say f of x is decreasing on negative infinity to 1, and f of x is increasing on 1 to positive infinity. This is your answer. Everything above is partial credit. You stating the intervals, the x values over which the function is decreasing or increasing, that's the answer. So that box is the answer. We were looking for intervals of increase and intervals of decrease of a function, and this box is the one that provides the answer to that question. The interval on which the function is decreasing and the one on which is increasing. Now, what do we get for free from this calculation? What do we get for free?
One is going to be the third test. So if 1 equals 0, then that's our critical point.
Very good. So what is that critical point? Minimum. See, last class, we had to do that annoying calculation to figure out what's minimum, what's maximum. Now you just see it. You see that the critical point at 1, as you mentioned, is a minimum. Because you see the function goes up and then it goes down. Right? It goes down, and then up. So here I'll put in blue for free, right? We have that at x equals 1, we have a minimum. And you can go and compute the y value if you're interested in a y value for that point by simply placing this into the original function, right? So you will find what the minimum value is. But the trick is that you instantly know that it's a minimum because you can see that it's a minimum. The function goes down and then it goes up, and it only does that when there is a minimum around. Let's take a look at another function. What else can we put here? Say f of x equals 3 over x. So take the derivative, right? What's the domain? For 3 over x. Excellent. Excellent. So the domain is from negative infinity to 0, union 0 to positive infinity. So we do have a vertical asymptote at x equals 0. So that's a partition point, right? And then do the derivative, set it equal to 0, see if you can find any other points. All right, let's take a look. So we have our f prime, the derivative, is negative 3 over x squared. When we set that equal to 0, we get negative 3 equal 0. Well, that's not true. since there is no solution, that means no critical points, and that means no min-max, right? The only point for us to partition is going to be the vertical asymptote at 0. We go from negative infinity to positive infinity, and then we pick 2 test points. You can pick anything you want inside each partition. So now I have the partition, I have my test points. So now the first derivative test, we take f prime at -1. Well, that's going to be -3 divided by -1 squared, which is -3, which is less than 0, which means that f of x is decreasing because it's less than 0. F prime at 1 is -3 over 1 squared, which is also -3, which is also less than 0. F of x is still less than 0. So now we can finally get the answer together. You can either say f of x, or you can say 3 over x is decreasing on negative infinity to 0, union 0 to infinity. We have to kick 0 out because there's a vertical asymptote there, so the function is not increasing or decreasing at that point. So we can't even talk about function being increasing or decreasing at a point, which is why all of the intervals are open intervals. But at the end, you have that the function is decreasing on the entire domain. Now, you know what the graph for 1 over x or 3 over x or 100 over x looks like. They're all the same, obviously. They look the same. So you can see that this function is always decreasing. You always go down as you're moving to the right. So the entire function is decreasing as you're moving along. And then there is that break at the horizontal asymptote, and then vertical asymptote, and then it restarts, right? So it's decreasing, and it's again decreasing. Questions, concerns?
Please just scroll up to the beginning of the part.
I mean, the beginning of the problem?
Yes.
Let's take a look at another example. So what was that? Oh, okay, no problems. Here we go. F of x equal sine 3x. Now, what's the domain of sine x, sine 3x, sine whatever x? Domain is? Yes, negative infinity to positive infinity. I did not restrict this to 0 to pi, 0 to 2 pi, or whatever. This means that you are going to have, because you know what the sign looks like, right? It's going to have infinitely many increases, infinitely many decreases, infinitely many max values, infinitely many min values, which means you have to involve the n to show the infinity in the answer. Let's see how that goes.
Professor, should we memorize the units for you now?
Yes, by now, sure. That was in Pre-Calc 2, which is a 3 course. I mean, depending on the major, because you always have access to your calculator, right? It's one thing that if you're in a major that will not use it later, for instance, one of my students who actually took Pre-Calc 2 with me, finished all the courses here, went to Cornell, and now he's working as a civil engineer building bridges. Well, he needs to know. Because it's much faster then, right? Now, there are majors that would still require calculus, but you will never use trig. For instance, business, right? Business would use some derivatives and so on for marginal cost, and we saw that in class, right? So in a business, you are still going to use it, but it will never be trig. So since you have access to the calculator, you know.
No, but like,
But
should we
the answer is
memorize it for the future exams and stuff like that have trig in it?
as I said, you always have your scientific calculator, right? So the answer is yes, but then you still have a calculator. So if you don't, you still have the way out.
Oh,
Depends on what you're going to use it later.
You can find the values with the calculator.
Yeah.
Yeah, it's got a converter if you want to.
It is very interesting for everyone to realize how meaningless exams and grades are once you are done with school. Completely pointless. Because the only thing that counts is what you know, nothing else. When you start working, it's the only thing that counts. All of my grades and all of my exams, if I don't know these things to teach it to you, right, I can't do the job. If the same thing if you're building a bridge or if you're building a new cell phone or whatever else you're doing, if you don't know stuff, you can have 7 4.0s and 13 PhDs. You are useless as anyone else who doesn't know. Nothing matters. As soon as you graduate and you start doing the work, the only thing here is to have some kind of resume and GPA and whatever to be granted the interview. And that's the end of it. After that, if you don't know stuff, you are useless. And that is the bottom line. So be wary of those with engineering degrees who never used trig or never used calculus in engineering. They're not engineers. All right, let's take a look. So f prime of x is equal to 3 cosine 3x. We said that equal to 0. The 3 will divide into 0 and will be gone. So all we have is cosine of 3x. Now, the cosine of 3x, well, first we need to see at which values cosine hits the 0. So when you draw the basic cosine, it hits at pi over 2 and 3 pi over 2. So for the principal period over here, we have that 3x is equal to pi over 2. and that 3x is equal to 3 pi over 2. When you divide both sides by 3, you get x is pi over 6, and you get that x is, you could cancel this, but trust me, don't. Just keep it as 3 pi over 6. Yes, it's pi over 2, but it's better if you leave it as 3 pi over 6 because you can see the values. So now, we see that, and then since this repeats, we can see that the distance between these two is 2 pi over 3. So the next one must be at 2 pi over 3, and then the next one has to be at 2 pi over 3, and so on. So there is a 2 pi over 3 gap, right, for each value. And there is also a 2 pi over 3 gap to the left. So we can start our partitions. We have infinitely many partitions, obviously. So if I start at pi over 6 and then 3 pi over 6, I have to add 2, so 5 pi over 6. The next one is at where? 7 pi, yes. You always add 2. You subtract into negative pi over 6. You subtract into negative 3 pi over 6, and so on. Infinitely many of these going to infinity, going to negative infinity with x values. So now, I know that my critical points are at pi over 6 plus 2n pi over 3. And n is there to give us the values that go to infinity, because that's the counter, right? So if n is, let's say, 2, then you have 2 times 2 is 4. You have 4 pi plus, and then you multiply by 2 for common denominator, so 8 pi plus pi would be 9 pi over 6. Good. Wait, hold on. It's not 2 pi over 3, it's 2 pi over 6. It's pi over 3. I'm not paying attention over here. You're not paying attention either. It's 2 pi over 6. It's pi over 3 is the 2 pi is the period for the whole thing. 2 pi over 3 is the period for the whole thing. This is 2 pi over 6. Okay. So now I need to pick a critical point. And this is why we did not cancel anything, because in between pi and 3 pi there is a value of 2 pi. So it's much easier to see the value in between, because this is pi, this is 3 pi. So what's in between pi and 3 pi? 2 pi, but that's only if the denominators are the same. It will be much harder for us to pick 2 pi over 6 as the middle if we went from pi over 6 to pi over 2. So okay, so what's between pi over 6 and pi over 2? Right? They don't have the same denominators, so it's much harder for us to pick. But if you keep all denominators the same at 6, in this case, right, they could be whatever the problem is. So in this case, if you pick and leave the denominator at 6, then you have the pi and then 3 pi, and then in between the 2 pi, and going from there, right, each one will have its own. So now, between 3 and 5, there is 4 pi over 6. And yes, they all do reduce, right, 6 pi over 6. Well, that's just pi, right? So we will use that in our first derivative test. We will use the simplified version. So our derivative here, so f prime at pi over 6, which is just pi over 3, right? 2 pi over 6 is pi over 3. And then we have, the derivative was 3 cosine 3x. 3 cosine of 3, and then you have your pi over 3. So those cancel. Cosine of pi is -1, so this is -3, less than 0, f of x decreasing. So the first one has decreased. Now this is a sine wave for the function, so obviously it's going to alternate. But we can just calculate one more because right, we can. That will be 2 pi over 3, which would be 3 cosine of 3 times 2 pi over 3. 3 is cancelled. Cosine of 2 pi is 1, so that's 3. That's larger than 0, and f of x is increasing. So they will alternate forever. And now, the tough part. Tough part is to write the answer, right? Because we need to put infinitely many of these, right, in one statement. So, f of x is increasing on, and now we pick one of the increase intervals. We can start at, let's say, negative pi over 6. So negative pi over 6 plus, and now we have our 2n pi over 6 to jump to next, right? So negative pi over 6 is one location, but then there is another one at 3 pi over 6, and there is another one at 7 pi over 6. So we have to jump to each one of those, and we jump by using 2n pi over 6, and it ends at pi over 6 plus 2n pi over 6. So these are the first x coordinate and the second for the interval. And now f of x is decreasing on, and now we have our pi over 6 plus 2n pi over 6, comma, 3 pi over 6 plus 2n pi over 6. And you could cancel now, because this is right the answer for the problem. Now is the time to cancel this 2 over 6 and put those n pi over 3s everywhere, because it's right. It's better to have the simplest form. So each one of these is now going to be n pi over 3, because we are just canceling and simplifying as much as we can. And that's the trig answer. Oh, we can also get min and max for free, right? Every minimum is at negative pi over 6 plus n pi over 3, and every maximum is at pi over 6 plus, right? So you can get min and max values for free. All right, one problem from the book for you to enjoy. And then we're going to talk about the second derivative test. So try this one on your own all the way through. So square root of x ln x. What is the domain of this? Anyone? Pre-calc 1. Square root of x ln x. So what is the domain? 0 to infinity. Good. We are not including the 0 because of ln. Okay. Have fun with that. the derivative and all of the good stuff up here, right? What kind of derivative? What kind of derivative we get to use? Yeah, the test on taking this type of the derivative is next week. I'm not asking you what's the solution to the problem. I'm just asking the most basic thing, what type of the derivative this is. Product rule. That's all I'm asking. That's all. This is on the test on Wednesday, right? Maybe with a cube on ln, like that. Just to find the derivative. Now, you have to find the derivative and then do the problem. And then we're going to double and triple on work in the next section. Now, we are only looking for the derivative. So f prime is what? Copy the first, derivative of the second, plus copy the second times the derivative of the first. And if we just write these as a single fraction, you don't have to rationalize, because once you set it equal to 0, you get to move one to the other side and then just cross multiply. So those square roots will straighten out anyway. So square root of x divided by x is equal to negative ln x over root x when you move the term to the right. And now when you cross multiply, you get x equals negative x ln x. Right? Square root of x times square root of x is just x. And we divide both sides by x. We know x is not 0 because of the domain. So we have 1 is equal to negative ln x. That means that ln x is equal to negative 1. And if you e both sides... Oh wait, what happened with my 2? I forgot the 2. I just noticed. So that 2 is going to go on this side. So it's going to be a 2 and a negative 2. There we go. So now when I e both sides, we have x equals e to the negative 2, which is 1 over e squared. Awesome. my partition starts at 0. There is nothing to the left because there is no domain, right? Domain starts at 0. And the partition is at 1 over e squared. And it's going to infinity. So we have two parts. We can pick two test points. The easy one over here, obviously, is going to be 1. The test point on the right, because 1 over e squared, 1 over whatever, is going to be less than 1. So that point is obvious. Now, a little bit trickier to pick a point between 0 and 1 over e squared, because you're not used to that. But when you know that in a fraction, if you make the denominator larger, you make the fraction smaller, it's easy to pick 1 over e cubed, because, right, e squared is smaller than e cubed, which means that the fraction 1 over e cubed is going to be smaller than 1 over e squared. So now we can do our first derivative test with f prime of 1 over e cubed. And my derivative was somewhere up there, square root of 1 over e cubed divided by 1 over e cubed plus ln of 1 over e cubed divided by 2 times the square root of 1 over e cubed. So we just need to calculate this. Now you can do that in a calculator, but you can also do it by carefully shoveling the algebra. So dealing with the double fraction on the first term, we get e cubed times the square root of 1 over e cubed. And on the second one, we are getting plus. The top is negative 3, because 1 over e the cubed is 1, it's 1 over e to the cubed is just e to the minus 3, and then ln and e cancel, so you just get negative 3 divided by 2 times the square root of 1 over e cubed. Now, to compute this further, we can have e cubed square root of 1 over e, well, we can just say e cubed divided by square root of e cubed, because the square root of 1 is just 1, minus 3 root e cubed, because we're going to bring that up for the double fraction, divided by 2. There we go. So now multiply, find the common denominator, which is 2 root e cubed. That's 2e cubed minus 3e cubed. And you see that this is negative e cubed divided by 2e cubed. All I need to know here is that I have a negative number divided by a positive number. I really don't care what the values are. All I know, it's a negative number divided by the positive number, which is going to be less than 0, and function is decreasing. Now, you could have plugged all of this in a calculator, but that kills the fun. So f prime at 1 is 1 over, so square root of 1 over 1 plus ln of 1 over 2 root 1, which is just 1, which is larger than 0. ln of 1 is 0, so that kills the second term completely, and you have square root of 1 divided by 1. So this is now f of x is increasing, and we get for free that we have a minimum at 1 over e squared. So I'll just say for free, minimum at x equals 1 over e squared. Now answer, this is what we are looking for. So f of x is decreasing on 0 to 1 over e squared, and f of x is increasing on 1 over e squared to positive infinity. That's it. That's the story of the first derivative test. Now we just need to talk about the second derivative, which will have identical calculation, different conclusion. Now, before we jump into mechanics and doing the problems, let me just put a title. Second derivative test, abbreviated as SDT. There we go. And now I want to invest the money in 3 portfolios. So we have the time, because money grows in time. We're going to invest 10K in each case, 10K of obviously money on the y-axis. So we're going to have three graphs over here. My first question is, which ones are making money as the time goes on, as you're looking at these? All of them. Perfect. Why? Because they're all increasing. As the time goes on, which is your x-axis, right? The y value, which represents the money, grows in time, right? So for each one of these graphs, they're all increasing functions, and all of these portfolios are making money. Are they all making the money at the same rate? Is there one that is better than the others? That's the question. Now, which one would that be? Which one do you want to stay away from? And which one you definitely want?
Stay away from the top.
Stay away from the top one. Very good. Because we see that in time, the earnings flatten, right? The earnings flatten, and that type of a graph could be good to describe population, for instance. Right? You start with some population, and then eventually it has to flatten like that because there will be no resources. You can't have infinitely many by population. If you have finite surface area, you have finite food, finite minerals, and everything else. So definitely, first one is not good for investing money. Which one is good? The bottom one, the number 3. Because that one is, as you can see, the time, as the time goes. So it starts earning money slowly. But then when it takes off, it makes money. Right, that's the one of those that it says, who has money makes money. So if you have money, right, you can make more money at the faster rate, right? Because that's the investments. So what we are learning now in our second derivative test is we are learning that the first graph will be called concave down. The one in the middle has no concavity, and the one on the bottom is concave up. And all they show is that the rate of change of increase is different. Now, I'm using the wording that says that the derivative of the derivative. Well, that's the second derivative, right? Because increase is calculated through the first derivative. We just did that, right? All of these are increasing. So since all of them are increasing, we know that the first derivative is larger than 0. But now we are talking about the rate of change of increase. Rate of change of increase is negative. Rate of change of increase is constant, means the second derivative is 0. And the rate of change of increase is positive, meaning concave up. So this gives us, now we understand what the concavity is, I hope, right? And now we're going to go if second derivative at the test point C is bigger than 0 on some interval a, b, which is again partition, then the f of x is concave up on that a-b interval. If f double prime of c is less than 0 on some a-b, then f of x is concave down on AB. And finally, this is now new, guys. If f double prime of c is equal to 0, we have what we call inflection point at x equals c. Inflection point over here, let me put the first cloud around this statement because this is your second derivative test. And now I'm going to point to inflection here, and I'm just going to say change in concavity. And we are going to understand this through the use of basic function x cubed. So inflection point is the point that we are using to separate concave up from concave down. I will also add the sentence, we partition over inflection points and vertical asymptotes. So vertical asymptotes is always with us. Let's understand this through f of x equals x cubed. So I have f of x equals x cubed, and we are going to use second derivative to find the intervals of concave up, concave down. Hold on. F prime of x is equal to 3x squared. Do we see that we are going to get x equals 0 for a critical point? Right? We see that. Now, we are also going to get x equals 0 for the inflection point because f double prime of x is 6x, and when you set that one equal to 0, you get x equals 0. So now you go, well, hold on, is this an inflection point or is it a critical point? Well, it's critical. It's inflection point. It is inflection point. They're stronger. Inflection point is the one where the concavity changes, and critical point is one where you have min and max. You know that x cubed, which is a squiggle like this, doesn't have min and max, but it does have the inflection point at the squiggle. So we know that this is good. So that's our inflection point. Now we're going to partition, and it only partitions at 0, right, from negative infinity to positive infinity. And we pick two test points. We can use -1 and 1 to be lazy. So now second derivative test as dt is going to be second derivative computed at -1. Well, second derivative computed at -1 is going to be 6 times -1, which is -6, which is less than 0, which means that f of x is concave down. Concave down on the part above -1. Second derivative at 1 is 6 times 1, which is 6. It's larger than 0. And then f of x is equal to concave up. Concave up. And now we can write the answer. And the answer says that f of x, you can also write x cubed, f of x is concave down on -infinity to 0, and f of x is concave up on 0 to infinity. This is the answer, and you see it looks pretty much the same as the one from first derivative test. So first derivative test deals with increase, decrease. Second derivative test deals with concavity. Identical calculations. One is using first derivative, the other one is using second derivative, but the calculations are identical. No difference. Yes?
If no one came to class, would you still give a lecture?
Of course, why not? If there was snow outside, I can still do the stream.
So you'll like teach your...
Oh, you mean there's absolutely no one in the classroom?
Yeah.
No, I'm still not at the point where I talk to myself. I would just link to the video from the other class because I already have. Yeah, I have so many of these.
Right.
I don't know if you check the 1400 videos. So my channel has this lecture covered at least 15 times.
Yeah.
Hour and a half, right? With different examples. So I can just list, like link in the announcement on Canvas. The lecture you guys missed today is 4.3. Next class, 4.4. Actually, that happened. One of my students, this was 4 years ago, one of my students transferred to NGIT in computer science department. He said, oh, I had this awesome math professor. He used to stream his lectures live. And the professor at NGIT said, oh, really? That sounds like a really cool idea. So they set up everything, and no one showed up for the class anymore. Immediately. I was like, wow, nice. As soon as they knew. It's an extra feature, but you can't really ask questions. It's good that you can rewind and you can really, you can see the same part 15 times. So it's a good resource tool, but you can't really ask questions. Plus, I'm not following the chat. So if I go and we have 4 people watching it live. Hi, people. See, it says 4 over there. 4 watching on top right. And they can type in chat. Probably now I was going to type something like hi or something. Anyway, so yeah. I would just have 2.5 hours off to do other stuff, and there will be a link to the lesson. Now let's take a look for the example in the book. Second derivative test. Some of these are absolute nightmare, which is amazing.
So we're not going to have an absolute nightmare one of the tests,
most likely. But then you can take your sweet time solving these. Like one of these problems, is x to the 4th divided by 2 minus 12x squared.
Fuck that.
That's a quotient rule followed by another quotient rule for a second derivative, right? It's a double quotient rule. So good luck with that. Let's take a look at x squared times e to the negative x. That doesn't look as threatening. Still, but it's still on calculations. It's going to probably take a while.
Is it illegal to upload these on Twitch?
Yes, unfortunately. I wanted to stream on Twitch. I asked them to create an education channel because they had a creative channel and they said, no, this is a gaming platform. I said, you have cooking shows and you have crafting shows, right, where people weave baskets. And then you have people streaming music, playing guitar, right? I want to stream calculus, and a lot of people on Twitch are, right, who use your platform are nerds, so they would definitely benefit if I do this there. And these idiots still said no. I said, okay, fine. Hi, YouTube.
You mentioned the baskets, and the constant thing for anyone with a humanities degree, something like that, is they got a degree in a basket. It's useless.
No, I actually seen the people weave baskets on Twitch. I watched them. And then they have instructional video, like Bob Ross videos are played there. Yeah, mostly as a meme, but sure. I mean, he did teach how to do painting, right? And people, So yes, there is a lot of creative stuff that was there, and I wanted to stream. Well, I did 2 streams under creative. And then they said, no, we'll ban your account if you continue streaming anything but a video game. Then someone told me, easy way to kind of do that is to still have a full screen calculus stream and then just put 7 by 10 pixel, video game in a corner, right? And you're covered. I just dumped them completely. I stream my video games on Mixer, and I stream educational stuff on YouTube, and I don't use Twitch at all anymore. Bye. That's the beauty of the free market. You always have alternatives. So their competitors are going to pick up the business on both of my.
I read this article recently about how those millennials are so enthralled with communism and socialism, and wanted to get rid of personal property.
The
less you know, the more it's.
The liberals think communism is a good idea, and we should give it a try.
They are not liberals.
No.
Those are opposing. It's the same thing like saying someone is fat and skinny at the same time. It's completely, you can't be 300 pounds and 90 pounds at the same time. It's impossible. There is nothing liberal and communism. They can't go in the same bag. They're polar opposites of each other. So that's the thing. You can be socialist and nationalist. That's what Hitler was, right? You can be communist and socialist. That's what Stalin was. But you can't be a liberal or a free market and a socialist. That's opposite, completely opposite. So, and it doesn't mix like colors. Anyway, people need to learn history a little bit. Anyway, well, let's take this beautiful problem. Do you want to approach this as a product rule, or do you want to approach it as a quotient rule? Because you can look at this as x squared over e to the x and use the quotient rule, or you can look at this as a product rule when you multiply them, right? So it's pick your poison, right? Whatever you like better. So generally people like product rule better. So, and the problem is posed in the book as a product rule. So we can just push through this and go with our first derivative as copy the first times the derivative of the second plus copy the second times the derivative of the first. Now remember what I said, if you learn to factor and simplify this, then chapter 4 will be easier, because we have to take another derivative of this to set it equal to 0, right? So we are going to factor this and simplify. We can kick out e to the negative, let's just kick out e to the negative. We could kick x as well, but just keep it because we don't want a triple product rule. In that case, you would have 3 functions. So just kick out e to the x, and what you're left is 2x minus x squared. All right, so it's still a product rule between 2 functions. If I kick an x out of the parentheses, which I can, then I would have 3 functions, and I have to use a formula that you don't know, which is called the triple product rule formula. It's different, right? So we're not going to do that. We're just going to keep these x's all on a pile in a polynomial, and then take another derivative here, and that is e to the negative x. So take the derivative here, which is 2 minus 2x, plus 2x minus x squared, and then minus e to the minus x. And now, when you simplify that one, you get e to the negative x, and then you have 2 minus 2x minus 2x plus x squared, because the minus from the second parenthesis would apply to those and then tally up over there. So we have now e to the negative x times x squared minus 4x plus 2. And what do we have now? Now we set this equal to 0. We set this one equal to 0, and we hope, right, to get at least 1 point something. But e to the negative x equals 0 has no solution. And it has no solution because they don't intersect. The function e to the minus x, right, is the decaying exponential, and the function x equals 0 is just a horizontal line at which is x-axis. They never intersect, and because they never intersect, they do not produce a solution. Now we have the x squared minus 4x plus 2 equal to 0. And for this one, if you can't factor, and in this case you can't, you have to use quadratic formula. When you use quadratic formula, you might run into the complex numbers. And in that case, there is no solution there either. And if you have no solution, and you have no inflection points, and you have no asymptotes, then the entire domain becomes a single partition. You pick any point, and you just do one calculation. So now let's see if we have anything here. What was the formula for anyone? Negative b plus minus. No, b squared. Minus 4ac, good. 2a, very good. All right, so we have negative b, that's going to be 4, plus minus square root of 16 minus 4ac, that will be 8, divided by 2. So 16, 4ac, good. So now this is 4 plus minus square root of 8 over 2, which is 2 plus minus root 2. Root 8 is 2 root 2, and then 2 will cancel with the 2 in the denominator, so we just have a root 2. So now, we have our partitions. there is a partition 2 minus root 2 and 2 plus root 2. We pick values. Obviously, number 2 is in between over here because 2 is the base, and then you take a little bit off and add a little bit on, right? So 2 has to be in between. Over here, if you want to be, right, this is a 0, and over here you can put 10, right? You can put 4. You can put 4 because root 2 is about 1.41, right? So you can say this is about 3.4. So you can put 4, but you can put 10, you can put 100, you can put 7 million, anything that is bigger than, right? So we actually have three parts. We are going from negative infinity to positive infinity. And we have to test second derivative test for 3 values now. So f prime, double prime of 0 is our first test point. And now we go and we look for our derivative. Now, look what our derivative is. It is, let me write it here. F double prime of x is equal to x squared minus 4x plus 2 divided by e to the x. So this is our derivative. And we know the denominator is always positive. So technically, all I need to do is to figure out whether the numerator is positive or negative. So when I plug in 0, I get 2 divided by a positive number, which is positive number divided by a positive number equals positive number, which is larger than 0. I don't care what these values are. I just need to know if they're bigger or smaller than 0. So if I can just not compute them, they'll be amazing. So when I plug in 0, x squared becomes 0 squared. So that's 0 minus 0 plus 2. So the numerator is 2. And denominator is always positive. E to the 0 is 1. So it's 2 over 1. The whole thing is 2. But we don't care the exact value. We just care that it's positive so we can say concave up. Next one. F double prime at 2. All right, what do I have? Well, I have 4 minus 8 plus 2 divided by a positive number. This is negative number divided by a positive number equals a negative number, less than 0, concave down. And finally, the f double prime of, I said 10, which is 100 minus 40 plus 2 divided by a positive number. And that's going to be 62. So that's positive divided by another positive is positive, and it's concave up. And that's it.
So your answer is just going to be between,
Yes.
0 and negative infinity, 0 to 2.
F of x is concave up on, and now we're going to negative infinity to 2 minus root 2 union 2 plus root 2 to positive infinity. F of x is concave down on 2 minus root 2, 2 plus root 2. And there we go. That's it. We have our intervals of concavity, and I'm going to just give you a few seconds, right, to write all of that stuff down, and I'm going to show you homework examples, right? I'm going to switch the screen to the book so you can see all different types of functions that you get to differentiate and solve equations with. right? Rather than, we're going to repeat all of these calculations in next section because this will be the part of the bigger problem. We're going to graph functions by hand in 4.4. And graphing functions by hand will involve you getting first and second derivative tests because you need to know on which intervals the function will go down, what intervals are going to go up. And you will be graphing all of these functions without the graphing utility. And then you can use the computer, obviously, to check your answers. Let's take a look at the problems. We are done. There's nothing else. This section was for first and second derivative tests, so we're just going to take a look at some of the problems in the book, and we'll go with the next section.